Okay, so we are going to start a brand new topic, and this is something in big data almost everybody is using. It's a very friendly system, lots of language support, good to use, and like it has a very good community. Okay, so it's evolving at very rapid rate. So the things that I'm going to cover. Most of the fundamentals today. And as you know that I told you, I promised you that there will be multiple hands-on session later on. So I will maybe next 2-3 lectures I will cover the fundamentals, and then there will be plenty of hands-on sessions on each of these things. Okay. All right. So let's get started. So I plan to cover the following things. The main abstraction for Spark is called the basically in-memory data processing, and you get to see how this is different from standard Hadoop, why this is good thing, and so on. So and then the main data structure or the main abstraction of data, the resilient distributed data set, which is the core of Spark that you deal with. Lineage graph I briefly touch upon, not much. Then you get to see this anatomy of Spark code with a couple of examples, followed by Spark operations and etc. Okay, so these are the kind of the broad plans. And in the next few lectures, we will take up the other important things, for example, processing graph using Spark, processing streaming data, and how to write iterative algorithms, iterative programs in Spark, and so on and so forth. Okay, so those are the things we're going to see in the next few lectures. But today, all about fundamentals and basics. Okay, so let's get started. Now, you know, MapReduce algorithms. Okay, so and by the way, I'm assuming that the data that you are keeping in distributed file systems, and you are using Hadoop. So Hadoop is basically also a storage system. So Spark also runs on Hadoop system as well. Okay, so you install the Hadoop cluster, Spark also runs on that. Spark has its own cluster as well, but mostly people use Hadoop cluster to run Spark. So no issue on that. Okay, only thing is that how you write the code. Okay, in Hadoop you standard like MapReduce you can write. In Spark you use, of course, you use MapReduce code, but in a different way. Okay, much more easy to handle, much more easy to write code, much more easy to understand, and all kinds of stuff. So let's try to understand this one. This is kind of the one of the key concept behind Spark. So if you have to write iterative algorithm, iterative program in MapReduce, what happens? Like most of the programs that you write, okay, for any real data is iterative in nature. That means you basically repeat the same kinds of state multiple times, okay, on a piece of data. Think about K-means clustering algorithm, okay. So you basically iterate over the data multiple times. Think about page rank, which we talked about. Okay, you compute the page rank values again and again and again. So you iterate over the entire graph. And most of these things that we know is this. Okay. Now here is the problem in standard MapReduce. So you have an input data which is sitting in distributed file system, DFS here. Okay. Now in the first iteration, MapReduce program has two components, map and reduce. Okay. So when you apply map operation, you have to read data from distributed file system. Okay, that's the way you do it. Then you reduce these things and so on and so forth. Once the reduce is done, then you write out the output of the reduce operations again to DFS. So DFS read coming into map, then after reduce, you writing out that into again DFS. So iteration 1 is done. Now iteration 2 starts. Again, you have to read from DFS, okay? Then you reduce, map and reduce, then you write the data into DFS, and so on and so forth. So if you have to run, for example, an algorithm for 10 iteration, okay? So 10 times you are doing read and write from DFS, okay? Now that is where the problem is. The problem is that if you have the simple standard file system that you have typically in your personal computers, then there won't be much problem. Okay. But reading and writing from DFS is a complicated business. Why? Because when you read, then the scheduler needs to tell you that, okay, these are the replications, so you read it from here. Somebody must tell you that, otherwise you end up reading same thing twice. Now, the writing is even more complicated because when you are writing it out, so there will be communication through the networks because you are replicating this data. Remember that you are writing to DFS, okay, not normal file system, DFS. So as a result, the replication is taking place. So replication means that the master node needs to make sure that it basically maintains a table telling that storing that where this particular chunk of data is going and where it is getting replicated. Then because you are replicating, there is a lots of communication through the network, okay, and lots of other things, synchronization, communication, all other things, okay. So therefore, it is not an easy thing to do, okay. Conceptually, it might be easy, but computationally and cost-wise, not an easy thing to do. These iterative algorithms in a MapReduce framework, okay. So that was one of the fundamental thing in standard MapReduce. Now, therefore, MapReduce is good for one pass computation. Okay, something like, for example, you want to do k-nearest neighbor, for instance. You have a simple data, okay, and you simply find out k-nearest neighbor. You simply take one pass and you basically figure out, okay, these are the k-nearest points. Good thing. But for multi-pass computation, for example, k-means, PageRank, and many other things that you know, this cannot be good thing. Or even stochastic gradient descent, okay, for training neural network. It's basically multi-pass algorithm, okay, you are taking the multiple pass about the data. So that is not a bad thing. Now, so basically the inefficient for multi-pass algorithms for this reason, which I mentioned, okay, that you are basically doing multiple reads and write to and from the DFS. The problem is basically there is no efficient mechanism for data sharing. You remember that you are operating your operations on the same piece of data again and again. Okay. Now, if you have difficulty understanding things, just keep in mind the k-means algorithm. Okay. Probably most of you know how k-means works. So you basically operating your thing on the same piece of data again and again. So the problem is there is no efficient mechanism for data sharing. Okay, you basically writing out things in distributed file systems, okay, and as a result, as you know, it's slow because of replications and disk storage and all kinds of stuff. Interestingly, most of the programs that we write, okay, in data-driven programs that we write, okay, so most of the time we spend on doing input and output operations. It's reading and writing the data, okay. Actual computation takes place very little. But most of the time we are doing reading and writing because huge amount of data. When you have huge amount of data, you mostly spend your time basically reading from disk, writing out to disk, and so on and so forth. But here is the problem. The problem is that despite knowing that almost 90% of time you are spending on input and output operations, okay, the MapReduce doesn't have very efficient mechanism for data sharing. Okay, and that is where the problem comes into picture. So the question is then, of course, where Spark is different from MapReduce, the fundamental difference. Okay. Again, I tell you that Spark is basically yet another MapReduce plus many other things. So it stands on same the MapReduce idea. So most of the time you basically do map and reduce operations, but it differently. But internally it handles these things in a very nice way, so that you can handle some of the problems that you are seeing in Spark in MapReduce, standard MapReduce. Okay, all right. So the first thing that Spark does, and I tell you, this is not always the case, but wherever you have that capacity, okay. So Spark uses an in-memory distributed data structure to store the data that is repeatedly used. Now, if you recall that in one of these lectures I mentioned, the amount of time that you spend for reading a chunk of data from disk and from main memory, RAM, is hugely different. So accessing data from RAM is much efficient compared to accessing data from disk. So what Spark tries to do, it basically tries to keep the piece of data that you want to repeatedly use in your computation into distributed main memory. We have talked about distributed file system in Hadoop, which is basically the things keeping your distributed hard disk, okay, in different machines. But in addition to that, here we also are bringing in new concept called distributed memory or in-memory distribution of data. Okay, so that is the one thing. And so this is a read-only data structure. Okay, that means you can, once you create it, you can only read from it. You cannot write into it. And there are reasons for that. The primary reason is that fault tolerance. So if you want to write, modify, and things like that, things become very complicated. So this is only read-only memory. So you can create new things from old things, but you can modify in place. Okay. Now, the second thing, what it does, of course, when you have that kind of setup, okay, say in-memory distributed data structure, and which is basically complicated. Now, if you have a single machine, some amount of RAM, you can create any amount of memory, whatever your system supports, you can do lots of operations so very easily. But when you have distributed memory, so as if there are 10 computers and your total memory is basically sum of all the memories of all the computers, so it will give you that whole memory to you, okay? And so because this is distributed memory, so handling things are very tricky, okay, if you write from scratch. And therefore, what Spark does, Spark provides very simple APIs, application programmer interfaces, okay, to access and create new data structure from the old one. Okay, so once you can create RDD, I will short form, I will use RDD. So you can create this kind of data structure, in-memory data structure, new. You can access the things very easily using like a couple of lines of codes, okay, using standard APIs, and you will see how we do that. Okay. And third, of course, you know, in any big data system involving like dozens and thousands of computers, failures are very common, which I mentioned, right? So fault tolerance is an important thing in any cluster computing framework. So therefore, in order to make things fault tolerant, okay, it maintains a lineage graph. So what is a lineage graph? Lineage graph essentially is nothing but, now when you're performing say 5 operations right from your input data, it remembers how you are creating every piece of data from the old data, from the original data. Why it is doing that? In case a particular node fails, say, then you are basically going to lose the data in that machine. So you need to recover that. Okay. Of course, you don't want to start computation again right from scratch for all the nodes. So you only want to do for that particular node. So what you do, the lineage graph, which is kind of a dependency graph, it remembers how you actually created all this data right from the beginning. So it will basically help you to figure out, okay, this piece of chunk of data, how I have created. So you, once a particular node fails, you can actually consult this lineage graph and again recompute only that particular structure. Okay, so that is how it basically recovers the lost data. All right. So what are the key features of Spark that which I mentioned? The in-memory data distribution, one of the most important features of Spark, and this is important for very fast data processing. Okay, you are not, if your memory permits, if you have plenty of memory, given that the amount of data that you have, you can probably keep everything in the main memory, and which basically makes things very, very fast. Okay, but remember that this is distributed main memory. This is the normal main memory that you have in standard computers. Second is efficient data loss recovery, which I mentioned using a lineage graph, very quickly recover a piece of chunk of data. Good thing for the programmer is that it has a very rich library. Okay, it has a graph library which is called GraphX. Okay, you can do lots of graph operations with a couple of lines of codes. Okay, which you otherwise have to do, like you have to write hundreds of lines of codes in say MapReduce and elsewhere. Okay, you also have a very rich machine learning library which is called MLib. And MLib provides most of these, nice functions, okay, for most of these well-known algorithms, okay. So what it does, you once you kind of call any function for machine learning, it will use this cluster computing framework to do things in parallel. So it is, you don't need to worry about it. You just like, to you, it's just like normal code. Now, structured query language, when you have to manipulate the structured database, like relational database and all, okay, it also provides some support from that, SQL, okay, you can do that also. Streaming data becoming very, very important nowadays because of the social media platforms where data has a velocity, is constantly coming in, constantly growing and all. So for streaming data, there are additional set of challenges that one has to tackle. And so those kind of challenges also are automatically tackled by, there is a streaming data kind of facilities, libraries in Spark. So which is basically you can make use of. Okay. So these are some of the libraries that we have. And there are many other things which we'll gradually talk about when we basically progress. Okay. And then you have multiple programming language support. You have Java, you have Scala, you have Python, you have even R. You can write codes in R in Spark. Okay, and so of course this main core of this system, Spark, is written in Scala, which runs on Java virtual machine. So you can interchangeably use Java and Scala. Within Scala code, you can call a Java function and so on and so forth. Okay, so that basically gives you lots of flexibility as a programmer. Okay. Another important thing is the interactive. Now, if you have little experience dealing with big data, okay, then debugging your code on big data is a very complicated thing. Okay, because it basically runs on a huge volume of data. Something is wrong, then it's basically difficult. And even debugging a code for cluster computer is then more difficult. Okay, so to ease that, you have the interactive facility. So you have an interactive shell, and we will, when we show the demo, you get to see how things actually happen. So you have the interactive shell where you don't have to write the whole set of codes like a main program and then you run it. What you can do, you can just execute one line at a time of the code and see the intermediate results and check it to make sure that the things are actually right. Okay. And then you basically proceed to the next. So one code at a time, one line at a time, you can execute the results and then move to the next one, see the results, and so on and so forth. So in this way, you can develop your codes in a modular fashion, and you can pinpoint at any point of time in any particular line of the code if things are going wrong. Okay, so these are some of the key features for Spark system. Okay, so I talked about the heart of Spark is bunch of APIs, application programmer interface. As a programmer, you are going to play with these APIs. Okay, so there are broadly two kinds of APIs: low-level API and high-level structured APIs. So low-level API, which I talked about, the core of Spark, which is resilient distributed dataset, and I will often refer to as RDD. Okay, so that's the core of Spark. So this is a very low-level API. And as a result, it gives lots of flexibility. Okay, you can basically create very nice things. Okay, in your own way, you can customize things in your own way by playing with these RDDs. Okay, but relatively non-trivial to write code for that. Okay, but you get lots of flexibilities for that. Now you have high-level structured APIs as well, and there are two things: data frame and data sets. So they are basically structured APIs. They have particular structure, mostly row and column kind of stuff. Okay. And you can basically specify some schema, table headers and all kinds of stuff, and they have their own functions to access data, to modify, to perform some operations, and so on and so forth. Okay, but the problem with that structured API is that sometimes when you have to play with different kind of situation, okay, and different kind of data, you may not have that kind of flexibility to write code that because of the limited this power and limited functionalities that is available with these APIs. So you want to fall back to RDD. So RDD is basically this thing. So internally, what happens that even if data frame and data sets, they are nice structured APIs, so they are essentially built on top of these RDDs. So RDDs are basically their foundations. So anything that you do, it basically goes to RDD, and then Spark basically executes the operations. Okay. So let's try to understand the key concept in Spark, which is resilient distributed dataset. Okay, and then in the next lecture we'll talk about the other two APIs. Okay, so what it is, okay, what it is, how it looks like, what can we do with that, and all kinds of stuff we're going to see. Okay, so first thing, that why it is called resilient. Okay, resilient in the sense that we can recompute missing or damaged partition due to node failure. Okay, that is why it is called resilient. Okay, you are not going to lose the data. We can very easily recompute it. Okay. Why distributed? Because the data residing on multiple nodes in a cluster. Okay, now basically, you can think about a chunk of data residing in multiple machines, multiple nodes in a cluster. And data set, as you know, is pretty trivial. Okay, so it's basically a collection of partitioned data with primitive values or any user-defined objects. But just like, if you have seen objects in Java or in Scala or structure in C programming language, okay, so things like that. So the objects could be, okay, the individual elements could be either the primitive values like integer, string, boolean, etc., or it could be any user-defined objects, okay, that you define. It could be word and count together or anything else that you like. So absolutely there is no restrictions. Okay. Now, here is kind of little example that you can see. Now, if I think like RDD of strings, for example, you can see that this one example that I am master, natural, student, and all, and you can see the one element. Similarly, RDD of pairs means word and count pairs. If you think about it, then you can go to say these things. So it looks like an array. Okay, so array of primitive elements or array of structured elements and things like this. Okay, but it's a distributed array. Okay, distributed array of objects or elements sitting across multiple nodes in a cluster. Okay, so if you really want to visualize this is not exactly the thing, not exactly the distributed array. There are lots of other things involved in it. But if you want to visualize the things, okay, so that's the way you can visualize it. Okay, now how it looks like, for example, again, this visualization is not exact picture because there are lots of other things with RDD. So, for example, think about you have n say cluster nodes, okay, in a cluster, okay, cluster of computers and cluster node. So you can think about this kind of partitioned array. Okay, it's a very big array partitioned, little piece of information in cluster node 1, cluster node 2, cluster node n, and so on and so forth. Okay, and so this way basically the Spark stores all this data as sort of as an RDD in a multiple nodes in the cluster. Okay, so as a programmer, of course, you want to know this Spark stack. Okay, what it offers for you. Okay, so here is the Spark stack. Okay, so let's start from the lowest level first, and then we gradually go up in this. So in the lowest level, of course, there is one more level which I omitted here. So which is basically your actual cluster, okay, cluster of computers. So you have the cluster of computers, and then you have different kind of cluster managers. So standalone scheduler, it could be Yarn, it could be Mesos. Okay, and let me tell you what they are actually. So of course you can run your Spark code in your single machine, okay, as a multi-threaded applications. Okay, and probably when you do your exercises and all, probably you will do that. Okay, same code that you can run on single machine or in cluster of computers. So when you are running your Spark code on in a single machine, the manager is basically standalone scheduler. Okay, it will manage all your resources for the Spark. Okay, so standalone scheduler will run. Now the situation changes when you run your code on actual cluster of computers. Then either you can use Yarn or Mesos. So Hadoop is basically managed by Yarn. Okay, yet another resource negotiator. So basically, you can use Yarn or there is another cluster manager called Mesos. So these are basically cluster managers, okay, which will manage the cluster, okay, on behalf of you. Okay, it's just like if you think in terms of like the for example, in standard programming concepts like the compilers. Okay, so it will kind of manage everything for you. Now on top of this, you have this Spark core. Okay, the actual Spark core. Okay, so what all this manipulation for RDDs and everything else, the main things that you see in this Spark core. Okay, and on top of this, you have several libraries. So which I briefly mentioned, like it could be Spark SQL for structured data, Spark Streaming for real-time data, machine learning for MLib, graphics for graph processing, and all kinds of stuff sitting there. Okay. So, and you probably will sit in that particular layer. Okay, as a user, as a programmer, you will sit there. Okay, you will probably access all these APIs and libraries. Okay, to do these things. Okay, so that is how basically, so whenever you are sending a request or writing a code, it will go through Spark core, followed by the resource manager. Okay, this particular resource manager. Then it will go to the operating systems of the individual computers, and then it will basically it will be run on the individual nodes of the clusters. Okay, so that is how basically things actually go. Okay. Now, one important thing in Spark, and which is kind of a driver for Spark, is called Spark context. Okay. So when you want to run a Spark code, the starting point for that is Spark context. Okay. So it basically tells Spark how to access a cluster. Okay. So when you enter into shell, for example, Scala shell or Python shell, okay, this Spark shell, so there is readily available variable called SC, which is short form for Spark context, is available to you, and you can basically use that to manipulate it. Or when you want to write the main program for that, you probably have to explicitly create Spark context, and we will see with real examples how we do that. Okay. And once the Spark context is created, you can use that Spark context to manipulate all other things, to create new variables, to create new RDDs, new operations, and all kinds of stuff. Okay, so that's really the starting point for all Spark program. Okay, right. Now here is a sort of this little thing that you probably will see. Okay, now both in Scala and Python I'm showing. So Scala shell, for example, this is the Scala shell. So once you are using Scala shell, you type the command SC, okay, and Spark is going to show something like this. Okay, and the numbers that you are seeing at the extreme right is basically because this is an object. Spark context is an object, so it is telling you the memory location of that the computer. Okay, that's it. So just where in which particular position of this memory it was created, so you are getting to know this memory location. Right. Now the master, another essential component in Spark is called master. Okay, and master basically, the master parameter for Spark context determines which cluster to use. Okay, so it tells you that which cluster to use. So you want to run it local mode, you want to use a particular cluster, and so on and so forth. So if you simply tell master to be local, then it runs Spark locally with only one worker thread, no parallelism, just like normal code that you write. Okay, if you mention say k, local k, then Spark will run your code locally, but with k worker threads and so on and so forth. Okay, and so depending upon that what this options would be, okay, the Spark or Mesos and things like this in master's argument, then it will basically run the appropriate cluster or local mode or things like this. Okay. So what does a master do? Okay. What's the main role of master? So master connects to a cluster manager, which in turn allocates the resources across the applications. Okay. So if you look at this little picture here, so your driver program, which is basically Spark context, the starting point of your Spark code, okay, it will interact with the cluster manager. Okay, and then cluster manager will interact with the worker nodes. Okay, so every worker node will have their executor, okay, which will execute the task, a particular task. You have little bit of cache, which is basically memory, which it will use for all intermediate computation and all. Okay, And of course, you know these worker nodes can listen to each other. Cluster manager, of course, will exchange things between worker nodes and so on and so forth. And of course, driver program will also know things from cluster managers. Okay, so driver program from cluster managers, and then driver programs, then to the cluster managers, then to the worker nodes, and so on and so forth. And that is how all the exchanges will take place into Spark computation. So important thing to remember is that Spark context will kick off everything for you. And that is why it is called the driver program. So it is driving all your computation. All right. Now, as a programmer, so you will be interested in how to write code, of course. Okay. So what are the main steps of a Spark program typically? Okay. In a sense, this is kind of a template when you want to write any Spark code. So what is the template? So template is basically, first of all, you have to create RDD from external data. Okay. So typically, external data means that either the data is in distributed file system or in local file system, somewhere sitting. Okay, in some file system your data is sitting. Okay, so you have to create an RDD from an external data. That's the first thing that you have to do. Okay, once you create it, then the second thing you do, and the colored words are basically the real kind of classification of the operations, and I will tell you in the next few slides what they actually mean and why they are done in that way. So first you create this from external data source. Okay, create an RDD. Then you do transformation operations, transform, and why it is done? Transform operation is done to define new RDDs. Okay. So from old RDDs to new RDDs, because the RDDs cannot be modified. Okay, you cannot modify in place an RDD like normal array or other things that you typically do in your standalone PC. You cannot do that. So the only way you can basically get new things by creating new RDD from the old RDD, and this is called transformation operation. Okay, so like map, filter, all kinds of stuff you're going to see. Then third important thing is that if necessary, this is not always necessary, if necessary, and this is one of the key features of Spark, which is basically storing in memory any intermediate RDDs that you will need to reuse again and again. Okay, you want to keep some part of the data into distributed memory, distributed RAM, that you think will be required by your program repeatedly. Okay, repeatedly, because then it basically can be accessed very quickly. So this is an optional thing depending upon what your requirement is, not on mandatory things. Okay, something like persist keyword, and we will show some examples of that later on. Okay, fourth step is the actual thing, which is basically launch actions. Okay, that means something that you want to see after that, the real results that you really care about. So these are called the action operations. Okay, so this action operation will actually kick off the parallel computation. Okay, that is when the actual computation will take place. Okay, so broadly these are like the 4 different steps that a typical Spark program will follow in that particular sequence. You may not have that sequence exactly as is. Sometimes you probably do not need to store into memory. Okay, sometimes you probably do not need to launch action operations always. You probably want to use it for other purposes and all kinds of stuff, and you will see for different things. So one such action operation, you can think about the count, for example. Okay, so you want to see the counts of, say, for example, words or count of some other things, and so that is when things will go, and we will tell you why there is this classification between transformation operation and action operation soon enough. So this is the same little picture again, just to remind you that the structure of this RDD when it is sitting in distributed memory. Okay, for simple visualization, for simplicity, assuming that this is a kind of distributed array or partitioned array, okay, sitting on multiple nodes in a cluster. Okay, that is it, and we want to manipulate this kind of structure. Okay, so next thing. Okay, so creating an RDD. Now we are getting into actual little codes now, how we do it. So creating an RDD. Okay? So broadly, two ways to do it. One, you can create an RDD by reading or loading data from an external source, which is disk. So this is called, and so I am using Scala codes here, little Scala things here. So it's pretty straightforward. So val means something like qualifier. Okay. So something like when you declare a variable in, say, in C or in Java, it's just like that, variable declaration. So val and then RDD. RDD is basically, it doesn't need to be an RDD. RDD in the sense that not the name, not necessarily be RDD. You can basically put any name here. So val RDD is equals to SC, which is basically Spark context, the driver program that I mentioned, and the Spark context will have lots of inbuilt functions. Okay, so sc.text file means that the function is text file. It will read data from a text file, which is sitting into input file or input file. Okay, that is it, simply. So what it will do, it will basically read data from input file, which is sitting somewhere, maybe in your local disk, depending upon what clusters that you're using, single machine or multiple machines or a distributed file system. Okay, and it will create an RDD called RDD. The name is RDD. Okay, all right. This is one way of creating these things. The second way of creating things is basically, and this is not, the second option is not really serves like the great purpose, but this is typically done to test your code quickly. Say you are writing some code and you want to test your code quickly, so you do that. So parallelizing a collection in your driver program, okay, in the main program. So how you do it? So val lines is sc.parallelize, then list this. There are basically two things that you are putting here. So essentially what you are doing, you are creating a list of two elements, pandas and I like pandas, and you are simply parallelizing the whole thing to create a new RDD. And these are the things that you do typically, like, you know, when you want to test your code quickly, something like when you are writing, say, little code to sort some numbers, you kind of generate some piece of numbers and then you sort it using your standard code in your standard programming exercises. It's something like that you do. Okay. So SC is basically Spark context, and which basically kicks up all these things for you. Right. Now, I mentioned that RDD for every operations that you have in Spark, they are classified into two categories. Okay, for RDD operations. So the transformation operation. Okay, example are map and filter and all, and there are many other transformation operations. Okay, we will see the list of all these things. And the action operation. Okay, so like count, save as text file, and stuff like this. Okay, so so the transformation operation, why? So the important question is why such a classification, okay, in Spark? Suddenly, why somebody needed to do all this? What is the benefit of that? Okay, so benefit is actually, great deal of benefit is there. And I tell you why. So let's talk about transformation operation. Okay, transformation operation is basically creating a new RDD from an old RDD. So it's like intermediate results. Okay, something like what you have seen in map phase in MapReduce. Okay, so, and that probably you don't really want to see the result. It will help you to produce something else. Okay, but the action operations are the ones which you really want to see. Okay, the results of which you really want to see at the end of it. Okay, so like counting things, so you want to see the counts of every words, or you want to save as text file the output of some certain part of code, and then basically you want to manipulate these things. Okay, so something that you want to see as a result of things is called action operation. Something which is basically intermediate things is called transformation operation. Okay? And there is a reason for that why they have done it. Okay, so the reason is that Spark follows a thing called lazy evaluation. So when you are typing a transformation operation, requesting a transformation operation, Spark will not do anything. It simply remembers what you want to do. When you are typing an action operation, trying to execute an action operation, only then it will go and kick off the computation for you. Okay, because you really want to see something out of it. And this is called lazy evaluation. Unless you give any action operation, Spark will not do anything. It will simply remember all other things for you. Okay. The reason is that if you, immediately upon seeing a particular transformation operation, you start your computation, then you have to do lots of internal things in a cluster. And if something goes wrong in between, you have to redo the whole thing again. Okay. So you do not want to do that. You want to wait until the last moment when you feel absolutely necessary to do something, you only do that. Okay, and you simply remembering how these basically codes are dependent on each other and using the lineage graph, and simply you execute that in that particular order. So quickly, some examples of RDD operations. Okay, so transformation operations, you create new data set from an existing one. That's the purpose. Okay, it's a new RDD from an existing RDD. That's what you do. So all transformation, as I mentioned, in Spark are lazy. Okay, so as I just briefly mentioned, that they do not compute the results right away. Simply you remember these things. Okay, and from the base data set. Okay. So you recompute, or you basically compute these things when an action is run on it. Okay, and it basically optimize the required computations and also recover from the lost data partitions. Okay, so here is a little example of actual code. Okay, let me tell you what it is. Say readme.md, which is typical readme format in GitHub, right? GitHub, when you are putting readme file in GitHub, you kind of create that file readme.md. Okay, so say this is a text file. Okay, and I want to do some kind of processing on it. Okay, so first line, if you look at it, val dist file is equals to sc.text file. So that means the first line is reading the file line by line from readme.md. Okay, then the next line of code, so you are applying map operation on it. So dist file.map, dist file is an RDD, and you can basically perform a map operation on it. So dist file.map, it is taking one line, then it is splitting that line, and then it is basically collecting these things. Okay, or dist file.flatMap, okay, from L to L.split.collect and other things that you could do. So essentially what you are doing, you are basically splitting these lines into words and then collecting this output into some other things. That's what you are doing. So just like, you know, splitting the lines into words, stream of words and things like this. So difference between map and flatMap is that map is one-on function, flatMap is one-to-many function. That's the only difference. Okay, and you'll get to see later on. So here, everything that you see, the 3 lines of code that you see here, and equivalently for Python, they're all transformation operation. There is no action operation on it. Okay, it's just like intermediate operation that you see. Okay. Right. Now, so these things that you are doing here, okay, is called the closures. Okay, so closure is essentially, you know, the piece of code that you want to run inside a particular function. Okay, and you can basically inline computation. Okay, you do not have that kind of support in many programming languages. For functional programming languages, you have that kind of support. Okay, so you can basically write any bunch of code inside that particular closure. Okay. Now actions. So actions is basically the operations that return an actual result. Okay, not the intermediate one, but the actual results that you really want to see or to care about. So, and therefore it picks up all the computation for you. Okay, and so here is a little example of action operation. Okay, so again, I have the same readme.md file. So first you are reading this file from your hard disk. Then you are applying some map operation to create a word and value. It's like word counting example I'm talking about. And then you are basically reducing by key. Reducing by key means I simply want to basically, you know, add all the frequencies of all the individual words. So words dot reduce by key, and this is the standard format, and you get to see this format of all these operations later on. I'm just giving this for an example. So words dot reduce by key will add the values, okay, for the words, okay, and then you simply collect and simply print for each println. finally you want to print it. So first line is an action operation, reading from file. Second line is a transformation operation, which you are basically taking individual lines, splitting them into words, and then emitting word and one, something like the word count that you have seen in Hadoop. And the third line is basically summing them up together. Okay, it's a reduce equivalent to MapReduce. Reduce by key. Here, key is the word, so you basically reduce by key, and then finally you want to print the results. So third line is basically an action operation because you want to see the result out of it. Okay. All right. Now, okay. Now, the typical anatomy of an RDD operation. Okay, what is the anatomy of it? So the typical thing is that the new RDD is equals to old RDD dot, say for example, map function, and inside this parenthesis, you write your own code. Okay. So you write any code inline. You simply type all the codes that you write, several lines of codes inside this parenthesis, or you can basically create a new function, okay, with all these lines of code that you write, and you can also call this function from inside this one. There are two ways you can do it. Just put all the codes inside this parenthesis, okay, or you can basically create a new function, okay, with your all these codes that you really want to run, and you call this function. Both are possible. Okay, you can do these things in Spark framework. Okay. Now I told you this one. I'm skipping this slide. So Spark follows lazy evaluation, and here it is again the same, like the code that I'm. For example, you have this file called data.txt. Okay, so you have 3 lines of code, 3 lines of data. You have I am here, she is there, you are there, and all. And so first line, for example, you are reading data from the data.text. So you are reading line by line. Then what you are doing? Then basically, if you look at this code very, very carefully, lines.map. So lines is basically my new RDD after the first line, and I'm applying map operation on it. So my map operation is essentially here is basically taking a single line, okay, and then from this it is producing s.length. That means it is producing the length of that line. Length of that line means in this case, like this is the number of characters in a particular line, okay, and then the total length is basically I'm trying to compute the total length. So line length dot reduce, and this is the reduce operation that you have here, a comma b to a plus b. So you're simply adding a set of numbers here. Okay, that's a standard reduce function that is available in Spark. You get to see such examples later on. Okay, so broadly, what I'm trying to do, I have a text file in my hard disk, and I want to basically see that the sum of lengths of all the line in my file, and that is exactly this code is actually doing. Okay, and as you know, we have mentioned that only in the third line, which is basically the action operation, upon seeing this third line, the final line, your Spark will start actual computation, not before that. Okay, otherwise it will simply remember. It will simply remember something like this, that total lengths depend on line lengths, line lengths depends on lines, lines depends on data.txt. So this way it will simply remember this dependency. And the moment it will see that there's a reduce operation I have to perform or action operation I have to perform, it will go and execute this operation in that sequence. Okay, so that's a little bit of code that basically you can probably want to experiment with, and we will basically see lots of complex code later on. Okay. Before I go into the next things, I think let's take a short break, and then we will come back and then talk about this some of these available RDD operations, okay, and how they actually work.